Okay. Capacitors separate charge. And that is, with the capacitor that we used for demonstration, we separate charge by using a Wimshurst generator, and we separate it using static electricity, meaning that we pull negative charges off of one plate and store them on the other plate, leaving positive charges behind. So we end up with a positively charged plate and a negatively charged plate. Capacitance is the ratio of charge to voltage. Okay, the more charge you can store for a given voltage, the greater the capacitance. For parallel plate capacitor, the voltage depends on the separation. I used A for the separation last time. The textbook uses D, and that's really better. Now I got confused by the A's, because as I said, I'm so way under the weather without really realizing. By Gauss's law, if these plates are much closer together than their dimensions, you have electric field of 4 pi k sigma. And excuse me, I kind of got 24-hour cases of hiccups. So interrupt myself in the middle of a word, that's the reason. Okay. At least usually that's the reason. Okay. So anyhow, you've got the electric field between these plates. The plates, if the plates are closer together, the electric field is spread out over a lesser distance, meaning you have less voltage. Okay. So the closer these plates are, the less the voltage. So in order to make the capacitor with a lot of capacitance, you want to have as little voltage as possible. So we want to move these plates close together. So that for the same amount of charge, of course, the amount of charge determines the density of charge on the two plates. That doesn't change with proximity of the plates. So for a given amount of charge, you reduce the voltage by moving the plates closer together, which increases your capacitance. All right. It takes energy to build up charge on a capacitor. And why is that? Well, let's just say we got this capacitor and it's uncharged. Okay, so uncharged. Now we move a little bit of charge. So with just a little bit of charge, maybe we have negative charge here and positive charge here. Okay, so we move a little bit of negative charge over here. don't have much field, we have just a little bit of voltage. Now, the next charge that we want to move is going to have to be moved against this voltage. So the next charge moves. And don't worry about where these charges are located here. This negative charge is just spread out over this whole plane. Okay. Negative charges repel each other, so they're going to get as far apart as possible. I don't want to draw a bunch of them because I want to represent a little bit of charge here. And the positive charge similarly would be distributed over the entire plane. So now it's like I've moved two little bits of charge. Another small charge has been transferred. Against the existing voltage. Okay, well, if the charge we transfer is delta Q, when the existing charge is Q, it requires some energy. Why? Because you've got a voltage between these plates, and if you transfer charge with a voltage between the plates, well, voltage is work per unit charge. So what we can say is capacitance is the amount of charge over the voltage. The voltage is Q over C. The energy required is delta Q times V. If you're going to ultimately build some charge, say Q max, you can add up the energies it takes to, well, transfer these small bits of charge. And what I wrote there is you have a C here. Okay. If you partition the Q interval from 0 up to Q max, this expression becomes what you integrate. And I probably don't know read to write this because I didn't plan well. Might be hard to read. This is 0 to Q max of Q over C. dq. So do that in a okay, so this is Q max squared over 2C. This is the energy that you have in a charged capacitor. So for example, if you're trying to use a capacitor to run a motor vehicle, something people have experimented with, you know what the capacitance is and how much charge you can store, you can calculate how much energy you have available. There's many more implications than that. You also have energy density. This is the energy with charged capacitors Q over 2C, where we don't really need to write the max on Q. Whatever the charge is, that's the energy. I use the max here to distinguish this Q from this Q. Just to make it clearer what you're doing with the interval. Okay, so there's the energy of your charged capacitor. You also have an energy density. If you divide this energy by the volume between the two plates, you have the energy per cubic meter, or energy per unit of volume, okay? And that's an important concept. All right. Does all that make sense? It's fairly straightforward. I ordinarily go into a little more detail with partitioning and so forth. I chose to wave my hands a little bit between this, and this, and this, and the interval, but it's pretty straightforward. Okay. Now we've talked about parallel plate capacitors. We can also have cylindrical and spherical capacitors. Anything that separates charge is going to give an electric field between the two separated charges. If we have a cylindrical capacitor, a cylinder inside a cylinder, we've got an inner cylinder of radius R1 and outer cylinder of radius R2. So we hook up our power source or our wind surge generator or whatever, and we separate charge between here and here. Say we pull off negative charge from the inner cylinder and put it on the outer cylinder, or vice versa. Then we have an electric field between the two cylinders. Okay, well, what is that electric field between the two cylinders? See if we can come up with that electric field. Okay. Well, to get the electric field between the two cylinders, we can always go back to Gauss's law. The total flux between cylinders is 4 pi k cubed. Also, the outer cylinder doesn't produce any flux inside of it. Okay. Flux comes from the charge inside the surface. Okay, so then we're talking about between the cylinders. So Gauss's law of flux is 4 pi k cubed. Radius of the Gaussian surface is r, where let's just make sure the Gaussian surface is between the inner and the outer sphere. The area of the surface is 2 pi RL. The field is 4 pi KQ over 2 pi RL, which is 2 KQ over R. Now to get we're going to do that at this point. So anyhow, there's a cylindrical capacitor, and there's the field between R1 and R2. Capacitance is C equals Q over V. This applies to any capacitor. Capacitance is always Q over V. We got to figure out V. How do we figure out V between here and here? It's not linear as with a parallel plate capacitor because you don't have a constant electric field. Well, to get your voltage then, you have to integrate your electric field. So your voltage is the integral from R1 to R2 of 2KQ over R, which is your electric field, with respect to R. You do that integral. Okay, now some people want to tell me that the antiderivative had a 1 over R squared in it. And that's, oh, that's a derivative. We're trying to integrate. Okay, so comes down to this, your voltage is the integral R1 to R2 up to KQ, which is your electric field, 2KQ over R, with respect to R, which is 2KQ times the natural log of the absolute value of R, evaluated between R1 and R2, which is 2KQ times the natural log of R2 minus the natural log of R1. And we don't worry about the absolute value because we're talking about a radius, which is always positive, okay? Radius is never negative. You might want to talk about a radius of 0, you've got a line, but you never talk about a negative radius. Okay, so, and then using properties of logarithms, you really want to stay familiar with. This is a natural log of R2 over R1. Now, something about this disturbing me a little bit. Because intuitively, I'm wondering, is length have anything to do with this? But no, the length, the Gaussian surface, you get the same electric field, no matter how short of a Gaussian surface you use here. And of course, we're ignoring edge effects. In other words, close to the edges out here, close to the ends of the capacitor. This really isn't your electric field. It's not radial anymore. Okay, so making an approximation. Make sure you read what your textbook has to say about that. So anyhow, there it is. 2KQ times the natural log of R2 over R1. And I'm pretty sure of that, but I'm going to take just a second since I'm not functioning at 100% and double check myself. Okay, so I double check. I believe this is right. So what's the capacitance? Can you write down the expression for the capacitance of this thing? Okay, now the thought I had earlier about L was correct. I thought L should be part of this. I mean, it's only common sense if you use common sense. the longer this thing is, the more charge it's gonna be able to hold for a given potential difference. And we see this L here, and I just write it down here. So I need an L here, and I need an L here, and I need an L in the denominator here, and an L in the denominator here, and an L in the denominator here. So when I calculate the capacitance, it's the total charge, which is Q, divided by what do I write? Pi over 2KQ over L times the natural log of R2 over R1. Q's divide out, I end up with an L in the numerator, not a 1. And then it's over okay, and the natural log of R2 over R1. And if I haven't left anything out, I'm going to check myself against the correct derivation. Yeah, now you'll see in your textbook an epsilon naught instead of a K. I mentioned before that 4 pi K is the reciprocal of epsilon naught. Okay. So that this K would come up into the numerator and you have some other stuff. So you can easily make that transfer. I've always used K because it's easy to remember. It's not easy to remember epsilon naught, although if I focused on it, I've got a pretty good memory for constants. I could easily remember it. The K is just so much easier, but I rebelled against that possibility. Epsilon naught's a good thing. It's permittivity, it's free space. And when you get into dielectrics, which we're going to do in a couple of minutes, it's a handy thing. Okay. All right. Well, anyhow, there it is. That's a capacitance of a cylindrical capacitor. If you want the energy it takes to charge this thing up, or the energy you can get by discharging it, it's going to be what else I did wrong there. Okay, Q squared over 2C. All right, we had a square on this thing. Obviously, there's got to be a square on this thing. I'm hoping that in a couple of days, less likely to be that. Okay. Okay. Now, dielectric. And one of the best dielectrics out there is water. What a dielectric does, you should be aware that water is a polar molecule. So if I have two plates of capacitor, and then in between those two plates, I had a sack of water. water polar molecules. The molecules on this side would have their positive ends facing the negative plate. And the molecules over this end would have the negative ends facing the positive plate. Does that make sense? I mean, negative is going to attract positive. If you got a water molecule, you got H2O. You've got an oxygen and a couple of hydrogens. I think it's 108-degree separation between these. Okay. And hydrogen, then the oxygen is going to be negative. Okay. They're sharing the electron from the hydrogen. So the single proton in the nucleus of the hydrogen is going to be fairly well unshielded, so it's going to tend to be positive. And you get extra negative charge on the oxygen. So that the positive ends, these molecules will be attracted to the negative end here, and negative end be attracted here. We're going to tend to align much like this. Of course, the molecules are much smaller than what I indicated. And then in between molecules might be an any orientation. In that case, what does that imply for the electric field between here and here? Well, if you do a Gaussian surface just inside this boundary here and this boundary here, you're not enclosing a whole lot of charge. So you don't get a whole lot of electric field. Another way to look at that is simply that the positive charges lined up along this end will tend to create an electric field in this direction, which opposes the electric field of these negative charges. So that you have much less electric field between the plates, meaning you have much less voltage between the plates. So the alignment for molecules tends to cancel out much of the electric field in place. So there's less voltage. Greater capacitance. So this is an example of a dielectric. And just capacitance. There are materials, water is not particularly convenient as a dielectric in a capacitor because it might be prone to leaking. Okay. And that would be pretty counterproductive. What you do is there are materials that behave in the same way. Okay, they're not liquids. And I don't know that much about the material properties. I've never really looked into it. But there are actually materials, that are insulating materials that behave the same way you have here. And you can put a very thin layer of that between two plates. So the plates are always right on top of each other. The distance between the plates is very small, which is going to tend to give you very little voltage. And then the dielectric maybe gives you 100 times less voltage than that. So that you can store a whole lot of charge for not all that much voltage. Well, that's the idea of the dielectric. And that's where the epsilon naught thing gets to be kind of useful. Okay. Your I don't know what you're about to connection. I don't think you'll have any trouble with it. If you do, let me know. Get it. Okay, so that's the whole idea of the dielectric. Well, that's pretty much what I wanted to talk about today, but since another problem I'm having today is I couldn't access the internet from home because Global Protect, which is basically protection software, wasn't working and I couldn't access the internet at all before I came in. So let me just take a look at what I might have missed here. Okay, I've not seen a whole lot that I didn't do or chose not to do. But two things. Strontium titanate has dielectric constant about 4 times that of water. And water is about 80. Strontium titanate's 310. Which means that if you have water between your two plates, you get 1/80th of the electric field, 1/80th of the voltage. Water is not practical. I don't know if strontium titanate is practical, but you would get 1/300th of the electric field, or 300 times capacitance by inserting strontium titanate if it's possible to do that. Now, the other thing in practical terms, if the electric field gets too strong, it'll gap through, it'll spark through your dielectric, okay? And that gets to what we call dielectric breakdown. Now, there's a table in your book over dielectric breakdown strengths. And I don't see strontium titanate here. Okay, so so, you know, typically dielectric breakdown occurs for insulating materials at electric fields around a few to several times 10 to the 7th newtons per coulomb. Just for comparison, between the plates of this capacitor we have here, we're probably getting 30,000 volts. Um, and we're not getting electric fields on the order of 10⁷ newtons per coulomb. A 30,000 volt field at a separation of 1 centimeter gives you about 10⁶, 3 times 10⁶ newtons per coulomb. So anyhow, okay, well, we have that. Dielectric breakdown again. You want a high dielectric breakdown strength. So that the plates are capacitive, don't gap through. Don't ionize and discharge through your dielectric.